If you have ever used a huge list in Python and wondered why your program became slow, generators can help. In this video, we will go through 15 real examples using yield so you can see exactly when generators make your code cleaner, faster, and more memory efficient. We start with the simplest generator pattern, producing values one at a time instead of building a full list first. In real code, this is useful when a sequence is needed step by step, like generating invoice numbers. Let's write count up to, use yield for each number, and then run the script to see the values appear during iteration. Let's break down why this works. The generator does not create a list of 5 numbers. It pauses at yield, hands one value to the for loop, and resumes only when the loop asks for the next value. Now we show the best habit for this pattern. Use generators for sequences that are consumed one item at a time. This keeps memory usage predictable and avoids building lists that the next step does not actually need. Next, we use generators with input streams, where loading everything at once can become expensive. In production, server logs can be much larger than memory-friendly examples. Here we create a small sample log, write read errors as a generator, and now we run it to print only the lines that contain angerer. Let's explain the result. The loop inside read errors receives one line, checks it, and either yields it or moves on. At no point do we keep the full file content as one big string or list. Now we show the best practice for files: stream when you only need to inspect or filter content. This is the right default for logs, exports, and other large text files. Now we move from raw streams to records, using generators to pass forward only the data that matters. Imagine we are preparing an email campaign and only active users should receive it. We write a small active users generator, then run the script and print the names that pass the filter. Let's break down the output. Ava and Mia have active set to true, so they are yielded. Ben and Noah are skipped, so the final loop never receives them. Now we show the best way to use this pattern. Keep the filter small and focused. That makes the next step simpler because it receives only the records it is supposed to handle. Generators are also useful for cleaning incoming data before the rest of the program sees it. In reports, CSV prices must behave like numbers, not text. We use dictReader, convert the price field to a float inside the generator, and now we run the code to print consistent product summaries. Let's explain why the output is clean. Each CSV row starts with price as a string, but the generator yields a dictionary where price is already a float. That is why the final print can format every value with 2 decimal places. Now we show the best practice for imported data. Normalize it as soon as it enters your code. This avoids repeated conversions and prevents later bugs caused by unexpected string values. Finally, we compose small generator steps into a readable pipeline. For order processing, we usually need several steps: remove canceled orders, read totals, and calculate revenue. Let's write 2 small generators, chain them together, and now run the script to see the completed order revenue. Let's unpack the pipeline. Sum asks order totals for numbers, order totals asks only completed for orders, and only completed yields only the 2 completed records. The canceled and pending orders never reach the revenue calculation. Now we show the best way to structure this. Keep each generator responsible for one transformation. That makes the pipeline readable and lets you test filtering and mapping separately. Now we move into external data streams, where generators are useful because the data usually arrives in pieces instead of all at once. When an API is paginated, you do not want every feature to repeat the same page number logic. Here we create a fake fetch page function, then iter customer starts at page 1, yields every customer, and follows the next pointer. Now we run the script and the caller sees one clean stream of customer names. Let's break down why this result is useful. The for loop at the bottom receives customers one at a time, even though the data originally lived across 3 separate API pages. Pagination becomes an implementation detail inside the generator. Now we show the best practice: expose paginated data as an iterator whenever the caller only needs the records. This keeps pagination control flow in one place and makes the rest of the application simpler to test and read. Next, we look at batch processing, where generators help us control memory while still sending data in useful chunks. When you send rows to a bulk insert or analytics API, one record at a time can be too slow. Here we write a batch generator that collects 3 rows, yields that list, and then starts a new list. Now we run it and watch how the final partial batch is still processed. Let's break down the output. The first two batches are full because they contain 3 rows each. The final batch only has 1 row, and the if batch check after the loop makes sure it still gets yielded. Now we show the best practice. Batch work, when each call has overhead. But keep the batch size explicit. This gives you fewer external calls without loading the entire dataset into memory. Now we switch to continuous data, where generators shine because they can calculate values as readings arrive. For lifestyle sensor data, we usually want a value as soon as enough readings exist. Here we keep a dequeue with a maximum size of 3, append each temperature, and yield an average once the window is full. Now we run the script and see the average update as new readings arrive. Let's break down why the first line appears at 902. With a window size of 3, the generator waits until it has readings from 900, 901, and 902. After that, the oldest value drops out automatically when a new reading is appended. Now we show the best practice. Keep only the state required for the current calculation. For rolling metrics, that usually means a small window, not a growing list of every reading ever received. Next, we handle nested data, where generators can turn complex structures into a simple sequence. Product catalogs often arrive as nested category lists, but many downstream tools want one category per line. Here we write a recursive generator. If the item is another list, we delegate to the same generator with yield from. Otherwise, we yield the category name. Now we run it and get a flat sequence. Let's break down why yield from is a good fit here. The recursive call already knows how to produce category names, so the outer generator can simply pass those values through. That keeps the code short and avoids manual nested loops for every depth. Now we show the best practice. Use yield from when your generator needs to forward values from another generator. It makes recursive traversal easier to read and keeps the focus on the shape of the data. Finally, in this batch, we use generators for text processing, turning raw lines into structured events one line at a time. Raw log lines are hard to work with, so we convert each valid line into a dictionary. The generator validates the number of fields, checks the status and response time, and skips malformed input. Now we run it and print only requests slower than 200 milliseconds. Let's break down the flow. Parse logs only turns valid text into structured events, and it does not decide what counts as slow. The for loop can then apply any threshold without changing the parse. Now we show the best practice. Separate parsing from filtering when building generator pipelines. Each stage should have one clear job, which makes the pipeline easier to test and rearrange. Now we move into coordinating streams. In real systems, data often arrives from different sources, but we still need to process it in one clean order. When audit data comes from an app and a payment system, we need one timeline, but we do not want to rebuild and sort a giant list. So we create 2 already sorted event streams, wrap eQPA merge inside audit trail, and yield each event as it becomes the next chronological item. Now we run the script and check the combined timeline. Let's break down why this works. eQPA merge assumes each input stream is already sorted, so it only compares the next available event from each stream. That gives us one ordered sequence while still keeping the processing lazy. Now we show the best practice. Use the standard library when the streams are already sorted. This is clearer than writing manual index logic, and it avoids collecting all events just to sort them again. Next, let's talk about cleanup. A generator may stop early, so resource handling code must still have a reliable exit path. In real code, a generator might read from a file, socket, or stream, and the caller may stop as soon as it finds one useful record. Here we simulate that resource, yield lines, break when we find an error, and then call close. Now we run it and watch the cleanup message appear. Let's break down the result. The loop stops after one consumed error line, so the generator is still paused inside its body. Calling close tells Python to terminate it, and the finally block runs before the generator is done. Now we show the best practice. Any generator that owns a resource should have a cleanup path. This matters most when consumers can break early, return early, or stop after the first match. Now we look at interactive generators. Most generators only send values out, but Python also lets us send values back in. For a running metric tracker, the generator needs to remember state and receive new transaction amounts. We start with total 0, yield it once, then each send call gives the generator the next amount to add. Now we run the script and see the cumulative totals. Let's break down the flow. Next primes the generator and stops at the first yield. After that, every send becomes the value of amount. The total is updated and the next yield returns the current state. Now we show the best practice. Use send only when two-way communication makes the stream easier to understand. If a normal function or class is clearer, choose that instead. Next is performance awareness. Generators are not automatically faster, but they are often much better for memory when data is large. In a migration script, building every ID up front can waste memory before real work even starts. Here we create the same range as a list and as a generator expression. Compare their object sizes with sys.getSideOf and then consume only 5 generated IDs. Now we run it and look at the difference. Let's break down what the output means. The list has already stored the whole sequence, while the generator only stores the recipe for producing the next value. That is why we can ask for 5 IDs without allocating the full result set as another list. Now we show the best practice. Use a generator when you only need to loop forward once. Use a list when you need indexing, repeated passes, sorting in place, or a stable snapshot. Finally, let's connect the ideas into a real workflow. A generator pipeline works best when every stage has one clear responsibility. For a real ETL workflow, generators let us pass records through small focused stages instead of building one huge function. We extract raw rows, validate them, transform amounts into floats, keep only one region, and batch rows before writing. Now we run the pipeline and inspect the simulated database writes. Let's break down why this shape works well. Validation removes broken rows early, transformation gives later stages clean types, filtering keeps only the target region, and batching controls how writes happen. Each stage can be tested by passing in a tiny iterable. Now we show the best practice. Keep each generator stage small and focused. That makes the workflow easier to debug, easier to replace, and easier to test with fake input rows. Now you have 15 practical patterns for using Python generators in real code. Like the video, subscribe to Dev Level Up, and write in the comments which Python topic or real-world example you want to see next.